All right, so now let's talk about some of the synthesis strategies that we've learned from the reactions that we've learned in this chapter. Particularly, what we learned last lecture is actually something that's going to be kind of very important, the different directings of these different groups, okay? What it means is that the order in which we perform these particular reactions is going to be very important. So let's take a look here. Let's say that I wanted to go from benzene to this 1-bromo 3-nitrobenzene here, or these two are in the meta position of one another. That means that whatever substituent I put on there first has to be meta-directing, right? And again, what I'm trying to emphasize here is that the order in which we carry out these two reactions is going to be really important. So in this particular case, I would first have to do the nitration reaction. That would give me my nitrobenzene, because the nitro group is a meta-director. So then when I add, second, when I add the Br2 in the presence of either the aluminum tribromide or the iron, I'm just gonna write the iron, I would get my desired product. Notice what would happen if I flip these. So let's say that first I did my bromination step. Okay. What's going to happen when I do my nitration step second? Oops. Well, bromine is an ortho or para-directing. And so in this case, let me actually make some room here. In this case, my products would be different. I would be getting, oops. The ortho mixture of the ortho and the para products. Okay, so the order in which I perform these two steps, the bromination and the nitration, they have to happen in a specific order in order to get the desired product. Okay, so the order in which we do things is going to be half the battle for this particular chapter. Another consideration is, what if we have multiple substituents already? Okay, so let's just take a look at this example here. What's going to happen? You just have to consider what your different groups are, right? So for the methyl group, I know that that's going to be an ortho as well as para-director, but the para position's already full, so can't do anything about that, right? So that's the direction that I get from my ortho-para, my methyl group rather. And then the nitro group is going to be meta-directing. So it's going to direct, these positions, okay? So sometimes your multiple substituents direct to the same position. Awesome. So then it's super easy to determine where your subsequent group is going to be added or substituted, I guess. But what happens if there's a conflict? So let's look at this case here. I want to figure out what happens when I nitrate this, 4-methylphenol or paramethylphenol. Here I have to consider the fact that the alcohol group is an ortho-para-director, so it wants to put substituents there. But the methyl group is also an ortho-para-director, so it wants to put the substituents there. Well, now I have to consider which one is the stronger activating group, right? My methyl group is just an alkyl group that's a weak activator compared to my alcohol group, which is a strong activator. So the strong win, and I would get nitration on that position that's ortho-para to the alcohol group. Okay, it's also not a bad idea to try to name these compounds. So, this is a skill that we learned before, but don't want to forget. Remember that this is my parent chain, this phenol group. And I have to count putting that parent chain at 1. So 1, 2, 3, 4. So a good thing to do is in this chapter throughout is to try to name these compounds. Not every single one we're going to be able to name, but some of them we can. In this case, we have the 2-nitro 4-methyl phenol. Okay. The other consideration, we talked about this a little bit, but just something to think about is the fact that we have the para position can be sterically hindered, right? So in this case, we have this alkyl group. It wants to direct to either the the ortho position is sterically hindered. It wants to direct to either the ortho or the para. But of course, because that ortho group is located next to this big bulky alkyl group, the para position is going to be preferred, and that's going to be my major product. So steric hindrance is something that we have to think about. So then let's say that we have, let's do this example here. We have these 2 alkyl groups, right? This one here is going to be directing to its ortho position. This one here is going to be directed to its ortho position. Both of these are the same sort of like strength. They're both weak activators. So who's going to win? Here, it's the sterics consideration that you want to make. It's going to go in whichever position's easier. They're both sort of the same favorability in terms of the weak activators, but one of them sterically hindered and one isn't. So there's going to be a preference for that non-sterically hindered product. Okay. The last consideration, I mean, this is actually just another sort of example. So let's go through again. Wants to direct here, here, here. And this is exactly how I would do these problems. Look at the group, look at the groups that are, look at where they're directing to, right? So I'm doing the same thing that I would kind of do in my head. This also wants to direct here, here, or here. So we have 2 equally weak activators directing all to the exact same carbons. So which one do we expect to actually be our major product? It's going to be that least sterically hindered position. And notice that you really don't get any when you put that nitrogen between those 2 bulky groups, that nitro group. Okay, but what if we want to force something to be in one of those sterically hindered positions? So this is this big bulky group. It's going to direct to the ortho or the para positions, but because it's so big and bulky, we would not expect those ortho positions to be substituted very easily. But how would, if this is my desired product, how could I go about forcing that? Well, we can use this strategy called a blocking group. Basically, we're going to block the para position such that the next substitution reaction that happens has to happen in that ortho position. Okay, so basically what I'm going to do first is I'm going to install a blocking group, and we'll talk about which group that is here in a second. But just notice that if I install that blocking group and then do the bromination step, the bromine has nowhere to go other than that ortho position. And then I'm going to remove the blocking group, okay? So this is the key features of a blocking group, is just something that I can add and then take off again. And this is where the reversibility of our sulfonation reaction comes into play. Okay, so this sulfonate group is going to be my blocking group. First, I would put it on using the fuming sulfuric acid. It's going to be directed to that para position because I have a big bulky substituent that's blocking the ortho position. Then I can go and do my bromination step. Now that bromine has no place to go other than to that ortho position. And then I can use the dilute sulfuric acid to remove the blocking group. Okay, so this blocking group strategy is something that you can do to get a product that would otherwise be sterically unfavored. There's actually another example of when you'll use it, and you'll see that in the discussion that's posted after this. So now, again, talking about synthesis strategies, there's another thing that's really important for our synthesis strategies. Remember, I told you when we first learned about this reaction here, the reduction of this nitro group, that it was going to play an important role in this chapter. Well, why is that? Well, because the nitro group is a strong deactivator and meta-directing, whereas the amine group is a strong activator, and it is ortho-para-directing. Okay, so this can be very important because if I, let's say that at the end of the day, I wanted like a bromoaniline or something like that. Well, if I wanted my bromine to be in the meta position, then I would want to make sure to do that reaction before this reduction. Whereas if I wanted it in the ortho-para position, I would do it after I did this reduction, right? So where do I do this reduction can influence the sort of products that you get. And we have a few that are like these. So first of all, the reduction of the nitro group, we also have the oxidation of the benzylic carbon, and that will change this from an ortho-para director to a meta director. We can reduce these acyl groups. We talked about this when we talked about the Friedel-Crafts reactions. We can reduce an acyl group to an alkyl group. That would change it from a meta director to an ortho-para director. And we can convert a methyl group to this tribromo group here. The methyl group would be an ortho-para director. Then we use excess NBS, convert it to this here. This is one of our strong deactivators and is meta-directing, okay? So again, let's just say that I wanted to go from benzene to bromobenzene here, or to, I'm sorry, this meta-bromoaniline, right? The problem here is that these two groups are located meta from one another, but they're both ortho-para directors. So that means that my first step is I'm going to do the, my first step, let's actually do this. This is my desired molecule here. First thing I'm going to do is do the nitration of the benzene. But now before reducing it to aniline, I'm going to brominate, because that will ensure that that bromine goes in the meta position. And then I can do reduce that nitro group to aniline. If I had switched when I did my reduction and my bromination, I would end up with the bromine in the ortho or the para position, right? So again, just trying to stress that order of when we do these reactions in this multi-step are going to be really important. Okay, I guess I just did basically that exact example there. Okay, here, you guys can on your own, let's say instead of it being in this position here, it's in this position here. It's a good practice problem to make sure you understand the point that's trying to be hammered home here about the order of when these reactions take place. Okay. Yeah, and it's just similar to before we were talking about how order matters. It's the same thing with these ones. This this is a kind of a really important slide here because these are groups that we can convert one orthopara director to a meta director or vice versa. So that's going to be something that's really powerful. Okay. Other random limitations that we have to consider. You cannot nitrate aniline. All right, by that, I mean we cannot do a nitration reaction on a molecule that also already on a benzene that already has an amino group. It turns out that it won't actually nitrate the ring. It will just oxidize the amine group back to a nitro group. The other thing is those Friedel-Crafts reactions. We had talked about how they don't work with nitrobenzene because it was deactivating. Now that we've learned how to categorize molecules as activators, deactivators, et cetera, we can sort of clarify this and say that the Friedel-Crafts reactions do not work with moderately or strongly deactivated rings. Okay, so just something to keep in mind.